Okay, so we want to look at magnetic fields. Now, normally what I would do is just do this all on paper. But with magnetic fields, we have this problem of visualization of the magnetic field. So I'm going to do this one on as a presentation and use a lot of great pictures, and hopefully we'll be okay. So magnets, how do they work? That's the joke. Okay, so let's start with the electric field. So if I have here on the left a single point charge, I get this pattern of field in space, electric field pointing out in all different directions. And so remember, this electric field is the force per unit charge. So if I put a charge at a particular location and I multiply that value of that charge by the vector value of the electric field, I'll get the force on that particle. So it's sort of like a force field. Now on the right, I have two charges, a positive and a negative, right next to each other. We call this an electric dipole. And so we get this different pattern of electric field around that will be important later. But now that we know something about the fields, let's look at magnetic fields. Here is one way that we can look at the magnetic field. Suppose you take a simple battery and a magnetic compass, and you connect a wire from one end of the battery to the other to make an electric current. Here's what happens. So I'm going to put the wire directly over the compass and hook up the battery, and you'll notice a deflection in the compass. So the compass points in the direction of the net magnetic field. So we have the Earth's magnetic field plus a magnetic field due to the wire, and you can see that the magnetic field due to the wire is significant and deflects that compass. If I run that compass through a piece of paper and put iron filings on there, the iron filings kind of line up in the direction of the magnetic field, and you can see the circular pattern around there. I just want you to show you that this is real stuff. It's not a super strong field to make a great pattern, but there is a slight circular pattern you can see there. But it's a 3D problem, and it's hard to draw on paper. Suppose I have this tiny little section of electric current, and in this case it's kind of coming out of the screen. That yellow wire is a small piece of electric current. It would make magnetic fields like these blue arrows, these cyan arrows, and you can see it has this circular pattern around the wire. We call this a curly magnetic field instead of the electric field due to a point charge which points radially outward. So this is different. This is the pattern of field for a simple piece of current. Now, there's this right-hand rule that allows us to find the direction of the magnetic field. If you put your thumb in the direction of the current from your right hand and wrap your hands around the wire, then it shows you the direction of those magnetic field lines. So in this case, I have the current, the conventional current, the flow of positive charge going to the left. That would make a magnetic field into the paper on the top and a magnetic field out of the paper on the bottom. I'm going to use the symbol B for magnetic field. And then we can draw these X with a circle around it to represent a vector going into the paper, and a dot with a circle around it to represent a vector coming out of the paper. That's like an arrow. Looking at the back of the arrow is for a vector going into the paper. And this is for the right hand. Okay, it's a right hand rule. There's many versions of the right hand rule, so just be careful. They always use the right hand. What if I have a single moving electric charge? So moving electric charge is an electric current. I can calculate the value of the magnetic field with this expression, which is kind of complicated. I get it. Okay, so here I have QV is the vector going to the right. I have a vector from the point charge to the place where I want to find the magnetic field, and that's the vector R. And then I can calculate the magnetic field with this constant mu naught over 4 pi. It's just a magnetic constant. And then I have the product QV cross R. So that's the vector cross product. So you can't multiply two vectors by each other. So we use the cross product in this case. It gives us a vector that's perpendicular to both QV and R. In this case, that vector would be coming out of the page. Now, a lot of times we don't want to deal with the vector nature of this cross product, so I can calculate the magnitude of the magnetic field as just the magnitude of QV times the magnitude of R times the sine of the angle between those two vectors, and then that gives me that too. Okay, but let's look at this cross product a little bit more. This is an animation of two vectors, vector A cross vector B, and it's in 3 dimensions, so you can see the problem. the resultant vector A cross B is always perpendicular to A and B. So that makes it a three-dimensional problem. You can't do this in 2D. We'll go over the right-hand rule about how to calculate that vector, but I just want to show you that it is indeed a 3D problem. What about the magnetic field due to a very, very long wire? So if the wire is infinitely long, it turns out that the magnetic field is always a perfect circle around the wire, and the magnitude of that field decreases with distance. So I can calculate that magnetic field as mu naught, that same constant, times the magnitude of the current divided by 2 pi r, where r is the distance from the wire to the magnetic field. So normally you would derive this, but you have to use calculus or a computer program to derive it. And so I'm just giving it to you. I'm giving it to you so that we can use this expression in different situations. What about a loop of wire? Suppose I have current going in the direction of the arrow, then it will make these right-hand rule circular magnetic fields, but everywhere in the loop, those magnetic fields point out of the paper and add up in the same direction. Outside of the loop, those magnetic fields are not as strong because they're more spread out. So this makes a very strong magnetic field inside the loop, not as strong outside. However, if you have a small loop and you plot the magnetic field at different positions around that loop, you get this pattern over here. And if you remember from that early slide, this looks like the magnetic field due to this looks like the electric field due to an electric dipole. So this looks like the same pattern of field and space as a dipole. And so a loop of wire can act as a magnetic dipole. That's important. If you want to just calculate the magnetic field in the center of the loop, then it's just mu naught I, where I is the current, over 2r, where r is the radius of the circle. So what about a bar magnet? How do they work? That's the famous question, right? Magnets, how do they work? Well, it's not so easy. You can see here that it does also produce a pattern of field and space that looks like a dipole. So maybe you could think that there are tiny little electric currents inside the magnet that make a dipole field, and that's how it works. That's not a bad idea, but where is this current in a bar magnet? The answer is not so simple. If you wanted to think about the magnetic field in a bar magnet as some type of atomic level electric current that makes it, I think that's okay. It's not exactly how it works, but that's not a bad way to think about it. It's a quantum mechanic effect at the atomic level. And I think that's about as good as we want for right now. We're not going to calculate magnetic fields due to bar magnets, but they do act like dipoles for most cases. What about the magnetic force? Here I have a wire hanging from these two clips that I can run electric current through, and it's right over a large magnet. So what happens when I connect the battery to the wire? I get a deflection in the wire. So I get anything that makes a magnetic field. If you put that in another magnetic field, it will experience a force. So here is an electric current carrying wire with a magnetic force acting on it. So how do we calculate the magnetic force on a wire? If I have a moving charge, then the magnetic force due to a magnetic field is going to be QV cross B. So this is not the magnetic field produced by the charge. It has to be some other magnetic field. So let's talk about these directions using the right-hand rule. Again, we have the cross product. So the magnetic force has to be perpendicular to both QV and B. And there's only two possible choices there. It could be, in this case, I'm showing magnetic field B is into the board, into the screen. So I could have a magnetic force going up, that's perpendicular to B and to QV, or I could have a magnetic force going down. Those are the two options. I can choose between those using the right-hand rule. Now there's a simplified version. If you look at your hand in this formation, your right hand, don't use your left. QV would be your index finger, B would be your middle finger, and your thumb of your right hand would be the direction of the force. So in this case, you can take your finger and point it to the right as you're looking at the screen, your finger is going into the paper, into the screen, and your thumb's pointing straight up. And that's how you can find the direction of that magnetic force on this moving charge. If you want to calculate the magnitude of that force, it would just be QV times the magnitude of B times the sine of the angle between them. In this situation, the angle between QV and B is 90, and the sine of 90 is 1. Be careful that the force deals with QV. If you have a negative charge, QV would be in the opposite direction of V. So just be careful with that. Don't ever try to use your left-hand rule for negative charges. Trust me, I thought that was a good idea. It's a bad idea. Just use your right hand. If you're right-handed, you always want to be putting down your pencil when you start doing the right-hand rule. Trust me. Experience says that's the best way to do it. Okay, what if I have a small piece of electric wire carrying current? It turns out that I times the length of that little tiny segment of wire is the same thing as QV. So I delta L, I'm using delta because it's small, is the same thing as QV, and I get the same expression for the magnetic force, except it's just I delta L cross B instead of QV cross B. But the direction's the same and everything. And now again, I is the direction of the conventional current. So that's the direction positive flow charge would be, not negative. Okay, so we don't always know if it's positive or negative charges moving. If you had electrons moving to the left in this picture, that would be a conventional current going to the right. Okay, so that's a brief introduction to the magnetic field and the magnetic force. And now we can use these ideas in other situations and do a lot of practice problems. I'll talk to you guys later.